Electric vehicles, or EVs, have gained widespread popularity in the past decade. They are seen as the future of transportation, playing a crucial role in combating climate change. With zero tailpipe emissions, reduced reliance on fossil fuels, and a smooth, noise-free drive, it's easy to understand why major global automotive companies are embracing electric technology. Numerous countries are setting ambitious goals to phase out internal combustion engine vehicles, leading to changes in our streets, cities, and homes to accommodate the electric revolution. From Norway, where 91% of new cars sold are electric, to China, the world's largest EV market, and the United States, where companies like Tesla drive innovation, the transition to an electrified future is a global endeavor. While we plug in our vehicles for charging and enjoy the quiet operation of electric motors, have we ever stopped to think about the true costs associated with creating these vehicles? Prominent commentator Tucker Carlson believes that EVs are a great disaster and the EV evolution is backed by the governments. In this video, we'll peel back the layers and reveal the concealed realities behind electric vehicles. We'll delve into the less-known aspects of EV production and ask, what sacrifice comes with this revolution? So, let's jump right into it. The electric vehicle we're talking about today has a history dating back to the 1800s. The journey began around 1832 when Robert Anderson created the first version of an electric vehicle. However, it wasn't until the 1870s that practical use became possible. Finally, in 1884, an English inventor successfully developed a functional electric vehicle, with a photograph still available. During this time, several electric vehicles were produced, but practical use faced challenges. The main obstacle was the need for batteries to power these vehicles. Crafting batteries turned out to be a complex task, contributing to the delayed practical application of electric vehicles. Also, the lack of infrastructure, especially the absence of charging stations, hindered widespread adoption during that period. When considering combustion engines, an average passenger vehicle releases about 4.6 metric tons of carbon dioxide in 1 year. With a typical lifespan of approximately 15 years, these petrol vehicles can accumulate a substantial 69 metric tons of carbon emissions during their operational period. Although diesel engines emit 40% less carbon dioxide than their petrol counterparts, their shorter lifespan of around 10 years leads to a continuous cycle of production and ongoing carbon emissions. Shifting our attention to electric vehicles, it's essential to recognize that they also produce carbon emissions, albeit at significantly lower levels compared to traditional combustion engines. The carbon footprint associated with electric vehicles is considerably reduced, providing a more environmentally friendly alternative in comparison to the continuous emissions from the production and operation of combustion engine vehicles. The typical lifespan of an electric vehicle ranges from 5 to 8 years, and with proper use, this period can potentially be prolonged. When looking at the carbon emissions linked to electric vehicles, a regular passenger vehicle with a 40 kilowatt battery produces approximately 2.3 metric tons of carbon dioxide, resulting in a total release of 4 to 5 metric tons during its operational life. For electric vehicles with larger batteries, like the 100 kilowatt batteries in models such as Tesla, the carbon emissions reach around 7 metric tons. Despite these emissions, when compared to the carbon footprint of petrol and diesel vehicles, electric vehicles exhibit a more environmentally friendly profile. Addressing the misconception that electric vehicles don't involve combustion, it's essential to understand the source of carbon emissions. While it's true that electric vehicles operate on batteries and don't produce fire or smoke in the traditional sense, carbon emissions still occur during the production and life cycle of the vehicle. To understand electric vehicles' inner workings, let's explore their construction and functionality. In the structure of an electric vehicle, the key element is the traction battery pack, which functions as the electrical storage system. This battery pack stores electricity in the form of DC current, powering the electric motors that drive the vehicle. Working in sync with this, the second crucial component is the DC converter. This converter ensures a consistent and efficient supply of current from the battery pack to the electric motor, adjusting based on the vehicle's needs. Comparing it to the energy-saving features of modern AC inverters, electric vehicles utilize similar technology. The third and essential part of an electric vehicle is the electric motor, serving as the central component. Its primary function is to convert electrical energy into kinetic energy, distinguishing electric vehicles from traditional ones. A notable feature of the electric motor is its regenerative braking system, aiding the vehicle in slowing down by transforming kinetic energy into another form and storing it for future use. Electric motors in vehicles typically fall into two categories: AC and DC. Another essential component is the power inverter, responsible for converting DC power back into AC power. This conversion facilitates the battery recharging process, crucial for the continuous operation of electric vehicles. Drawing a parallel, this is similar to the self-start mechanism in two-wheelers and three-wheelers, where a small battery, usually lasting 3 to 4 years, is utilized. Initiating the vehicle through self-start leads to the battery recharging by converting energy, a mechanism familiar in conventional vehicles. In the realm of electric vehicles, this process operates on a larger scale, where the same battery powers the vehicle for movement and is subsequently recharged during its operation. The need for periodic recharging arises because the energy used for vehicle movement isn't enough to fully recharge the battery. To address this, the next crucial part comes into play: the charger port. This is the designated space where the electric plug is inserted, initiating the recharging process for the vehicle's battery. Besides these, electric vehicles use other components like the onboard charger, controller, and auxiliary batteries. Since the battery is a central and significant part of an electric vehicle, it naturally incurs a high cost. About 40% of the total cost of an electric vehicle is attributed to its battery. For example, if a car costs $1 million, 40% of that amount goes to the battery. The high cost of the battery is due to its components, mainly composed of lithium, cobalt, graphite, nickel, and manganese. These materials contribute to the functionality and efficiency of the battery, but their cost affects the overall affordability of electric vehicles. Lithium is a crucial element in electric vehicle batteries thanks to its unique properties. As the lightest metal on the periodic table, lithium provides benefits like being lightweight, having an extended lifespan, and offering high power capacity. These qualities make it an ideal choice for electric vehicle applications. Cobalt plays a vital role in ensuring structural stability for lithium, thereby enhancing overall battery performance and safety. The widespread use of lithium is evident in most batteries, commonly known as lithium-ion batteries. Despite their common use, lithium batteries are recognized for their high cost, mainly due to the intricate and challenging process of lithium extraction. Unlike petrol and diesel extracted from the deep sea, lithium and cobalt are mined and taken from the ground. This extraction process is not only complex, but also has significant social and environmental implications, putting the well-being of individuals involved in these activities at risk. In regions of Africa where cobalt extraction occurs, there's a troubling reliance on child labor. Children as young as 12 to 14 are sent deep into the ground to retrieve rocks, exposing them to significant risks. These rocks are then processed and cobalt is extracted. Shockingly, some reports highlight the loss of children's lives during such activities. The compensation for this risky work is minimal, often accounting to $1 to $2 per day. The exploitation of these young lives for cobalt production raises ethical and humanitarian concerns. Beyond the human toll, the extraction of lithium and cobalt is environmentally harmful. The process contributes to pollution, contaminating both soil and air during extraction. Construction, a major contributor to pollution, is identified in reports as a key source. Similarly, mining minerals exacerbate environmental pollution on a large scale, emphasizing the need for sustainable practices in obtaining these essential components for electric vehicles. When examining the lithium manufacturing process, it becomes clear that it not only causes soil and air contamination, but also has a considerable water footprint. Producing just 1 ton of lithium requires a substantial 2 million liters of water. While electric vehicles are often promoted as environmentally friendly, the energy source for recharging, typically electricity, introduces environmental concerns. The environmental impact of electric vehicles is closely tied to how electricity is generated. Ideally, using green energy sources like hydroelectric or wind power would support the idea of a green revolution. However, in many countries, including ours, there's a significant reliance on coal for electricity generation, raising questions about the overall environmental friendliness of electric vehicles. The necessary shift to electric vehicles is crucial, But a comprehensive approach requires simultaneously establishing an ecosystem that promotes sustained green electricity production. By adopting renewable energy sources, we can make the powering of electric vehicles more sustainable and address the global carbon footprint. However, it's crucial to recognize that the growing demand for electric batteries, mainly those using lithium, presents challenges regarding resource consumption and environmental impact. Lithium primarily comes from countries with significant reserves. Major contributors to lithium production are Bolivia, Argentina, the US, Chile, Australia, and China. Reports indicate that Bolivia has the highest lithium reserves globally, with an impressive 21 million tons. Australia follows closely with around 7 billion tons, and China holds a noteworthy 4.5 million tons. Despite Bolivia having ample reserves, Australia is the leading producer of lithium, contributing approximately 56,000 tons annually. In contrast, Bolivia's actual lithium production is relatively lower. Chile also plays a significant role, producing around 26,000 tons yearly. China adds to the global supply chain with 14,000 tons of lithium production, though on a somewhat smaller scale than Australia. This global distribution highlights the complex dynamics of lithium extraction and production. The primary drawback of electric vehicles is their limited driving range and the associated challenge of charging infrastructure. Despite improvements in battery technology enhancing EV ranges, they still fall short compared to traditional internal combustion vehicles. EVs often encounter range anxiety, a concern about not having enough battery charge to reach the intended destination. The current charging infrastructure also poses a challenge. Although efforts are being made to expand charging networks globally, it is not as ubiquitous as traditional fuel stations. This can be especially problematic for long-distance travel, where finding charging stations might be challenging. Additionally, the time required to charge an electric vehicle, even with fast charging options, is significantly longer than the time it takes to refuel a traditional vehicle with gasoline or diesel. This inconvenience can discourage potential EV adopters, particularly those who rely on their vehicles for frequent and long-distance travel. One significant drawback of electric vehicles is their higher initial cost, which can impede widespread adoption. The main factor contributing to this elevated initial cost is the advanced battery technology used in electric vehicles. Lithium-ion batteries, commonly found in EVs, are costly to manufacture. The expenses stem from raw materials like lithium, cobalt, and nickel. While technological advancements and economies of scale are gradually lowering battery costs, they still constitute a substantial portion of an electric vehicle's price. Recognizing the importance of transitioning to electric vehicles for environmental sustainability, governments worldwide provide incentives and subsidies to encourage consumer adoption. These measures aim to offset the upfront expenses, making electric vehicles more financially accessible. Incentives may take the form of tax credits, rebates, grants, and special privileges, such as access to carpool lanes. While the initial price tag of an electric vehicle might be higher than that of a traditional gas-powered one, looking at the total cost of ownership over the vehicle's lifespan tells a different story. Electric vehicles typically come with lower operating costs thanks to fewer moving parts, reduced maintenance needs, and lower energy expenses. Over time, these factors can offset or even outweigh the higher upfront expense. Affordability poses a significant challenge to the widespread adoption of electric vehicles, particularly for consumers with limited financial resources. Despite the potential for long-term savings and operational costs, the perception of a steep initial cost can discourage many potential buyers. Addressing these affordability concerns involves not only cutting the starting price, but also educating consumers about the overall economic advantages of owning an electric vehicle. Affordability in electric vehicles is also influenced by the potential decline of their batteries over time. Although manufacturers are enhancing battery durability, worries about degradation and the eventual need for battery replacement persist. The substantial cost of replacing a battery can impact the overall economic feasibility of the vehicle for consumers. It is crucial for manufacturers and policymakers to focus on advancing battery technology to improve lifespan and reduce replacement costs. As electric vehicles become more common, the electronic waste generated by their batteries poses a unique challenge. Despite having a longer lifespan than conventional vehicle batteries, EV batteries eventually reach the end of their usable life. Disposing of and recycling these large and complex batteries raises environmental concerns and logistical challenges. Electric vehicle batteries, mainly lithium-ion batteries, are intricate systems with a mix of materials. Recycling these batteries to recover valuable metals like lithium, cobalt, and nickel is a complicated process. There's a concern about limited recycling facilities capable of handling the diverse and large-scale nature of EV batteries. Improper disposal or insufficient recycling could result in environmental contamination and health risks. Developing safe and effective methods for managing and recycling these hazardous components is essential to minimize potential negative impacts. Transporting used EV batteries to recycling facilities adds another layer of complexity. With the increasing number of electric vehicles, the volume of batteries for recycling also rises. Establishing a sustainable and efficient logistics network for transporting used batteries to recycling centers without compromising safety and environmental standards remains an ongoing challenge. The absence of a standardized recycling process for electric vehicle batteries poses a challenge. Various manufacturers employ different battery chemistries, designs, and materials. This lack of uniformity complicates the development of universal recycling methods, necessitating specialized processes for each battery type. This highlights the importance of a cohesive, industry-wide approach. Some initiatives consider giving used electric vehicle batteries a second life by repurposing them for stationary energy storage. While this can prolong the battery's useful life, it eventually adds complexity to the end-of-life stage. Managing batteries that have served both in vehicles and stationary applications raises questions about efficient recycling once their second life concludes. The resale value of electric vehicles presents a notable drawback in the automotive landscape. Unlike traditional internal combustion engine vehicles, EVs encounter challenges in maintaining a competitive resale value. One significant factor contributing to this disadvantage is the rapid evolution of electric vehicle technology. As newer models with improved features and battery technologies emerge, older EVs can quickly become outdated, leading to a decline in their resale value. The key element affecting EV resale value is the battery. Over time, lithium-ion batteries commonly used in EVs undergo degradation, resulting in reduced capacity and performance. Potential buyers often express concerns about the battery's longevity and the associated costs of replacement. In contrast to conventional vehicles, where components like engines may have longer lifespans, the perceived vulnerability of EV batteries can negatively impact their resale value. Furthermore, the changing infrastructure for electric vehicle charging contributes to the challenge of resale value. With the expansion and improvement of charging infrastructure, older EVs may encounter compatibility issues with newer charging technologies. This can diminish the appeal of older models for potential buyers, leading to a decline in resale value. Market dynamics also play a role. While the demand for EVs is gradually rising, the used EV market is still in its development stage. As the market matures and more pre-owned EVs become accessible, competitive pricing pressures may further impact the resale value of older models. Unlike traditional vehicles benefiting from a well-established used car market, EVs may experience less stable resale values due to a narrower pool of buyers and fewer established pricing benchmarks. Consumer opinions and awareness also play a role in influencing the resale value of electric vehicles. Misunderstandings about battery life, charging infrastructure, and overall reliability of EVs can create reservations among potential buyers. Addressing these misconceptions takes time and education, indirectly impacting the resale value of current EVs as the market adapts to a more knowledgeable consumer base. Government incentives and policies can have both positive and negative impacts on EV resale value. While incentives might initially boost new EV purchases, the subsequent surplus in the used market could result in a decrease in resale value. On the flip side, changes in government policies, such as reductions in incentives or adjustments to regulations, can affect buyer confidence and influence the resale value of existing EVs. Another drawback is the limited variety of models compared to the wide range available in the traditional internal combustion engine vehicle market. While EVs are gaining popularity, the diversity in models and body types remains somewhat restricted, presenting a challenge for consumers looking for options that match their specific preferences and needs. One reason for the limited model availability is the relatively recent mainstream adoption of electric vehicles. As the automotive industry shifts towards electrification, manufacturers are gradually expanding their offerings in EVs. However, creating new models involves extensive research, development, and testing processes, leading to a slower pace compared to the well-established and diverse lineup of traditional vehicles. The lack of variety in electric vehicle models is particularly noticeable in specific categories like SUVs and trucks. These segments, traditionally offering numerous choices in the conventional vehicle markets, currently provide a more limited selection of electric options. This constraint could pose a significant disadvantage for consumers who prioritize features, space, and capabilities associated with SUVs or trucks, potentially steering them towards traditional vehicles instead of electric alternatives. Another factor contributing to the limited models is the inherent challenges in designing and manufacturing electric vehicles. EVs often demand unique engineering considerations, especially regarding the integration of batteries and electric drivetrains. Manufacturers need to invest considerable resources in developing platforms that accommodate these components, while meeting safety standards and performance requirements. This complex development process can lead to a slower introduction of new models compared to the more straightforward production of conventional vehicles. Moreover, the current emphasis on specific market segments, like compact cars and sedans, results in gaps in electric options for consumers with diverse preferences. While these smaller electric vehicles may be suitable for urban commuters and environmentally conscious individuals, those desiring larger vehicles or specific functionalities might find their choices restricted. The constrained availability of models also intersects with consumer preferences and regional demands. Different markets exhibit varying needs and preferences, and the existing range of EV models may not align with the requirements of certain regions or demographics. Manufacturers must carefully assess market demands and adjust production accordingly, contributing to the slower expansion of available EV models. Another factor to consider is the impact of economies of scale on EV production. Mass producing a variety of models necessitates significant upfront investments and the ability to achieve economies of scale for cost-effective production. As the EV market grows, manufacturers may gain the necessary scale to diversify their offerings. Until then, the limited models remain a notable disadvantage. Government policies and regulations can both facilitate and hinder the expansion of EV models. Incentives for manufacturers to invest in electric vehicle development and production can accelerate the introduction of new models. Conversely, stringent regulations or limited support may slow down the process, restricting the options available to consumers. That's all we've got for this topic. Thanks for watching, and stay tuned.